Hello, everyone, and welcome to today's webinar, Building Decarbonization Tech Series, Modeling Deep Commercial Retrofits. My name is Katie Kaluzny. I'm the Associate Director at the Illinois Green Alliance, and we're really excited to be putting on this program for you today. Today's program was put on by the Illinois Green Alliance's Programs Committee. It's a volunteer group that coordinates educational events covering a wide range of topics throughout the year for the green building industry. And this Building Decarb Tech series is something we've been doing throughout the year since March. This is the final event in the series and also our final education event for Illinois Green for the year. So we're pretty excited for you all to be joining us today to talk about commercial retrofits. You've all been muted upon entry, so please type any questions you have into the chat or Q&A, and we'll get them answered at the end. The Illinois Green Alliance is a membership-driven nonprofit organization that advances green buildings and sustainable communities for all. Our 5-year strategic plan pushes the green building industry to get on the path to net zero, and we achieve this work through educational events such as panels and building tours, by engaging the community and partnering with organizations across Illinois, and by advocating for new policies and legislation. You can view all of our past webinars in our on-demand webinar library if you want to catch up on what you've missed throughout the year. I want to take a moment to recognize Illinois Green Alliance's sustaining sponsors who make our work possible, and a special thank you to our gold level sponsors, ComEd, Resource Innovations, and Sloan. You can make a commitment to advance green buildings and sustainable communities across the state, and if you want to, you can always contact us about sponsorship and partnership at illinoisgreenalliance.org/sponsorship. And now I'd love to talk about our great lineup of speakers for today's program. We have Alan May from Cyclone Energy Group. And Alan leads Cyclone's effort in building simulations and analytics, such as energy modeling, daylight analysis, computational fluid dynamics, two-dimensional thermal transmission modeling, hydrothermal analysis, refrigeration modeling, and geothermal studies. Very impressive, Alan. He oversees the technical aspect of all simulation projects and mentors junior engineers. He works very closely with architects, MEP engineers, and project managers on large-scale commercial and industrial buildings and plants. Our second speaker today is Akram Ali from the Argonne National Laboratory. He is an embedded systems engineer at Argonne's Electric Vehicle Smart Grid Interoperability Center. He has a PhD in architectural engineering from Illinois Institute of Technology and has several years of experience in designing low power wireless sensors and controls. He has developed solutions for retrofitting legacy building systems such as radiators with smart controls, and is currently working to develop solutions that will allow using the next generation of electric vehicles as power storage for buildings using vehicle to grid technology. And finally, we have Graham Linn. Graham is the president of HabLab, a building performance consulting firm he founded in 2021. HabLab's mission is to enable healthy and delightful buildings that make the lowest possible carbon commitment. Graham has worked in building performance for 10 years, and prior to this, he served in the US Air Force as an engineer in the research laboratory focused on scramjet engines. Graham has been on the board of the Wisconsin chapter of the International Building Performance and Simulation Association since 2018. And our moderator for today's program is Jed Starner with Cyclone Energy Group. Jed is also a member of the Illinois Greens Programs Committee who helped organize this program. And I'm excited to turn it over to Jed to intro the program and also facilitate the Q&A after the program concludes. So take it away, Jed.
Thanks, Katie. I'm pretty excited to talk about this subject. We got Graham's item and put together this tech series for today. So existing buildings are going to be something that we continually need to work on, and trying to find the right data to efficiently solve our problems to make these buildings better moving forward is going to be our challenge. So how we efficiently do this with each building's unique challenges, collecting data, simulating, putting pieces together. So I'm pretty excited. I think we're going to keep building on this energy modeling tech series piece. So it's pretty exciting. Alan's going to give a nice talk of 2 case studies to look at some of the challenges of existing building central plants. And then we're going to have a nice overview of some sensor technologies that have been used to collect information. And then Graham's got a great case study to look at some unique challenges with building envelope and mechanical systems and how simulations can help figure out solutions and paths forward. And with that, we're going to turn it over to Alan on our first presentation.
All right, thanks for the introduction, Katie and Jen. So today I'm going to talk about energy modeling tool for retrofit, and I'm going to review the methodology and look at 2 projects. Let's get this started. We already did the introduction, some examples my group does. And today's learning objectives, I'm going to talk about energy modeling. What is it? And we're going to look at using energy modeling for existing buildings. What is the process and why we use it? And then we're going to showcase a central plan retrofit project. And we're going to showcase a commercial office retrofit. Obviously, we're going to talk about lessons learned, how we're going to make the process better. So what is energy modeling? I know we have a lot of modelers in the audience, and energy modeling has been a very common and popular practice for new constructions. But I think it's nice to do a high-level overview. What is it, and what goes into it, and what's the effort, and what's the process? So imagine you have a building. All right, you have the location, the building located somewhere, let's say in Chicago. You're going to perform the building against the weather. You have envelope, and you have MEP systems. You have plug loads, process loads, and you operate the building a certain way. And your tenants use the building a certain way, and there is a control logic on your MEP system. And your occupant has certain behaviors, right? All those are inputs in the energy model. You can input those in the model and simulate against certain logics and principles. And those principles can be control logic, can be weather, simulate against the weather, and the logic can be solar, heat transfer, thermodynamics, operation, a bunch of stuff. And you can use commercial tools. There are lots of commercial tools out there, and you can program. When I was at school, I used to program actually. And then once you set this up, and you can simulate, and you can get a bunch of outputs. And what are the outputs? You can get temperature, you can get consumption, cost, loads, operational loads. Why that is important? Because often, if you look at mechanical design or electrical design, often you just look at a point of time number, right? Meaning their number often is just a point of time in a year. The energy model can give you a period of time, meaning for 8,760 hours in a year profile. You can look at system performance. You can look at carbon emissions. Pretty much anything that's related to building operations. And how do you use that to simulate an existing building? I'm showing you a model we built in the past. You have this existing building, and we built a very representative geometry. Basically, it is a digital twin. So what is a digital twin? Digital twin is you have something in reality. You have a building somewhere, and you're building a digital copy of it to make it as representative as possible, meaning you can simulate the operation of that reality. And why it is valuable, because often for large scale, let's say for this size of building, if you want to do something, if you want to replace a plant, right? If you want to replace a chiller, replace a boiler, it is significant effort. And you want to do a very comprehensive study before you make that decision. And energy model, obviously, you don't have to touch it. You just, created this digital twin and do all those studies in that model and see the impact and see if your investment is worth it or not. There are guidelines out there how you should do this. What is the accuracy? What is the bias? That is ASHRAE guideline 14. It is a comprehensive. Why it's comprehensive? Because the energy model can simulate the interaction between envelope and your internal gains and the operation, how you use the building, and how the mechanical system or electrical system respond to your user profile. So, which is important for building operations. Let's say if you replace lighting, right? And you can do hand calcs, you can do manual calculation, hey, what's the saving? But lighting fixture release heat into the space. That part is very hard to manually calculate. How do you calculate lighting? The mechanical system, the response in terms of, less or more heat gains from lights, and the energy model can do that. What is the process? When you thinking about a retrofit, when you're starting a project, you have to define the scope, right? What exactly you want to do? You want to replace a chiller or replace a boiler, or you just want to optimize some controls. Obviously to calibrate, you need a bunch of information, a lot of information. You have to collect utility data. You have to go on site, talk to people, talk to the building engineer, and take pictures of the equipment, and take screenshots of your building automation system. If you have data logs, collect that data as well, and model or build the digital twin, meaning geometry, envelope, usage, all bunch of stuff we mentioned previously. And you're going to simulate your setup against historical weather, meaning that was real weather data. And then you calibrate your model to the existing condition, meaning it is as representative as possible. You try to match the building operation. Obviously, when the model is set up, and then you can implement what you want to do, right? You want to replace the chiller, then you build a new chiller plant in your model and just see the difference between your new chiller plant versus the existing, right? You see the how much it's going to reduce the load, how much is going to save you in terms of dollar, and obviously you can calculate carbon emissions and you can calculate returns. I'm going to show you two case studies. The first one is a campus retrofit project. I'm going to start with a question, more of a logic test. I know our industry is talking about electrification, but there is some resistance because still as of today, gas is a lot cheaper than electricity. In terms of cheaper, we're looking at per kBTU basis. We're looking at the cost at the same unit. Gas is cheaper, but what if I want to electrify, but I would still want to pay less money? How can we do that? And we're going to come back to this question after we review this project. So what is this scope? It's a pretty typical campus central plant. It's a combined heat and power plant, meaning they have gas turbine and they have steam generator. And then they have all bunch of chillers and they have cooling towers, they have thermal energy storage, TES. And very common setup for campus, for universities is that if you have steam on site, you generate steam for electricity, you have steam turbine chillers. You can use the steam to run chiller for cooling application. So the plant provide central chilled water, provide hot water, and generates electricity for all campus buildings. But at the same time, the university obviously still purchase electricity and gas from utility companies. That's the existing condition. And what is the retrofit scope? The retrofit scope is to get rid of most of the centrifugal chillers, which is electrical driven. Replace them with heat recovery chillers and add geothermal field, meaning you couple the heat recovery chiller with geothermal. And they are going to add all bunch of PV panels on campus. So what does this retrofit do, right? Obviously, heat recovery chillers are electric, right? It can do heating and cooling, and has simultaneous heating and cooling as well. So this slide is to show my fellow energy modelers, and I know some of you guys probably have the same type of project and same scope, and I wanted to show you guys my process, how I approach this project, and how I analyze the setup. So basically, I have heating and load profile for all the campus buildings that connect to the central plant, right? It has consistent heating and cooling load, simultaneous heating and cooling load, significant cooling load in summer, and some minor heating load in summer as well. And I imported this load profile to the simulation to IES we use, and then I set up the plan, set up the central plan, and I set up the logic, how you're going to run those equipment, the sequence and the logic. And then obviously, once you set up the plan, you have the load profile. You can simulate your plan against the load profile. You're going to generate all bunch of profiles. That is load against power consumption, right? If you have your load and then you have your power consumption profile, what you can do is that you can calculate efficiencies. You can calculate 8,760 hours COP numbers. And then obviously the university is installing significant amount of PV, and PV going to have impact on the system, right? Especially in a region that you do not have net metering, that you're going to use the PV differently than you want to use the PV as much as possible on site. So we can add PV to that power profile, and we can study the impact of using PV. Obviously, this study, you're going to have all kinds of profiles. And from those profiles, you can calculate efficiencies. You can calculate how much money you're going to pay to run this equipment. And you can calculate carbon emissions, which is important for this university. And obviously, you can calculate return of investment, right? Those equipment are not cheap. And going back to this question I asked, right? How do you beat gas? If you electrify, how do you beat it? And here is an example. Here's the calculation behind it. So if you purchase electricity at almost 6 cents per kWh and you purchase gas at 45 cents per CERM, if you calculate per kBTU basis, gas is 3.8 times more expensive, cheaper. Meaning, how do you beat it, right? You have to have electrical equipment that efficiency that is high enough, then you can beat the cost, obviously. In this case, right, you have to have a COP of 2.58 to beat the gas equipment. And can you do that in this retrofit? Yes, you can. You can run the heat recovery chillers. I call them heat pump chillers. And as long as the heating and cooling COP is high enough, in this case, it is high enough. And, those are the dollars, $165,000 for March, for January, versus if you run a steam heating, you're going to pay $212,000. Obviously, if you want the all electric application is cheaper in this case. And the result of this retrofit, the cooling plan efficiency going to increase by 36%. Heating can be all electric, and the COP is 4.7. That is very significant. But keep in mind, this is a heat recovery chiller. It has simultaneous heating and cooling, and it is coupled with geo. So this 4.7 is high, but it's uncommon. compared to, air source heat pump type of application. And obviously CO2e decreased by 40% without PV and 67% with PV. That is very, very significant. And case study number 2, I'm going to look at a office retrofit. This is a very large scale 1.5 million square foot office tower in one of the major cities, and it has EUI of 250. A newer office, you will be looking at EUI from 30 to 100, depends on how you use it and what are the tenants, right? But this building has EUI of 250. Obviously, that is too high, and that if there is something going on with the local laws or local building performance standards, you're going to get penalized, and that is very significant. That is why they try to do retrofits in this case. And a very common setup, they have centrifugal chiller. In this case, they also have steam turbine chillers, and they have steam to hot water exchanger, meaning you're going to use steam to generate hot water. They have cooling towers, and they have on the air side, they have air handling units plus fan power boxes and VAV boxes for the office space. Very, very common setup for office type of buildings. And what is the problem, right? What is the problem? What happens when you have 30 tenants in this 1.5 million square foot building? What happens, right? Each tenant gonna have their own requirement for the base building service they receive. If someone, just one single tenant says, hey, I want a 42 Fahrenheit chilled water, then the building going to supply 42 Fahrenheit chilled water all the time. There is no reset, right? Obviously, if you want to run your chiller that way, it's not going to be efficient, but that is a tenant requirement, and you have to do that for the entire building. And if you have 30 tenants, they're going to use their building differently, right? They're going to use their space differently. The landlord often has very limited control over how tenants use their space. You would think the tenants shut off their lights, turn off their laptops, and turn off their printers, all the miscellaneous equipment when they leave the office space. Think again sometimes, for this project, we had a reality check, meaning, what we wished versus what we got was very different. Tenants do not shut off their lights, and tenants have servers, computers run 24/7 nonstop. And another problem is, what if you have steam turbine chillers? And those chillers, they have COP of 1. If you're lucky, you have a COP of 1. The reason why people use those is because you can, avoid the demand charge in summer, and gas is cheap, and even you have low COP, you still pay less money. But the problem is EUI is going to be super high if you have a COP of 1. And I'm not going to talk too much about simulation. I'm going to talk about solutions here. So for this project, we're going to get rid of those steam turbine chillers. That is, leading to high EUIs. We're going to replace those chillers with MAC bearing chillers, which are going to have at least COP of 5.5 to 6, which is very good. We're going to replace the steam to hot water exchanger to on-site gas fire condensing boilers. That's 95% efficiency. With this size of this scale of building, obviously, electrification can be very challenging, but it's still an option. We're going to make sure the building engineers implement some controls, right? When you leave the building, when it's occupied, you should shut off your outside air intake, and you should set back the set points don't run the building at 70 Fahrenheit when no one is there, right? In winter. And some very simple and straightforward and effective retrofit, that is lighting retrofit, replace lighting fixtures, put occupancy sensors and controls in place. And another one very effective measure is to put signs, right, at the switch. Turn off the lights when you not use the space. Lessons learned for large scale commercial retrofits is very challenging. It is very challenging. You're going to deal with a lot of people, a lot of files, a lot of information. My takeaway from my past retrofit project is be very clear who is who when you deal with so many people, and make sure you know where to get the key information. And often, because the building engineers, they run the building 365 days a year. They know they're building the best. They have the most information. The building engineer might be your best friend. And when you go on site, take as many pictures as possible, because when you go back and sit in front of your laptop, you forget things and you don't remember what equipment you look at, what's the capacity, what's the nameplate, right? You can't remember those. Take pictures, make notes, keep them organized. You can find those things, And to my fellow modelers, often, for retrofit projects, it's pretty frustrating sometimes. You're not going to get all the information. There are hundreds, sometimes thousands of inputs into the model. You're not going to get all the information. 100%, you're not going to get all the information. So make reasonable assumptions, and show your client your assumptions, discuss the assumptions, and don't be surprised when you hear something that's completely uncommon. You never know, people have preference how they run their buildings, and you never know how they're going to do that. So communication is key. And lastly, but most importantly, you have to enjoy the process, right? It is a very challenging process, but it is very fun. It is an adventure. So that concludes my presentation today. I'm going to turn this over to Akron.
Thanks, Alan. Hold on, I'm trying to share my screen. Can you guys hear me? I'm not sure if my voice is clear enough. Okay, perfect. So my name is Akram Ali. So my topic is going to be about advancing open source tools for indoor environmental monitoring and building system control using wireless sensor networks. A lot of this research was done at the Built Environment Research Group at Illinois Institute of Technology. Let's start off with a quick introduction. Basically, we all know that buildings waste a lot of energy, basically largest consumers of energy, and a lot of it is wasted in unoccupied spaces and improper installation, which is even more prevalent now after the pandemic and during the pandemic. But usually detecting and remediation of this energy waste requires understanding the complex relationship between all these different variables that go on inside buildings, right? And we also know from annual energy outlook of US EIA that building energy use is predicted to increase in the next few decades as the population and floor space grows. Residential a little bit, but commercial exponentially. But newer energy efficient buildings, they kind of offset this energy use a little bit. However, the problem is the new construction only contributes to a very small portion of the entire overall building stock. This obviously changes based on recession, inflation, and a lot of factors, but most of the buildings in operation today are quite old, especially in the United States, right? Renovating older buildings with new technologies usually has a high cost to it. What I mean by renovating is ripping out existing systems and, installing new ones. Sometimes it's not even possible. So it's important to develop methods of new methods of how to retrofit inside these buildings so we can adapt to it and then also account for new construction. If you look at some commercial building systems that exist, building systems that you can, I'm sorry, I'm in presenter view. Hold on, I just saw that. Sorry about that. Second. Sorry, all these problems have to happen today. Okay, how's it now? Good, perfect. All right. Okay. So we have a lot of commercial solutions. I'm sure some of you have seen these around. A lot of these can go from low cost to high cost that control legacy systems, and you can install this in new buildings. But what happens is older buildings, like legacy systems such as radiator controls or pneumatic controls or cast iron radiators, all of these usually cannot be retrofitted with those kind of technologies. You have to do some kind of modifications. Sometimes you just can't because of health issues like asbestos. You can't just go out ripping the ceiling floor or ceiling tiles. You can't just replace the entire. So what they do is you just seal off this whole area and try to install over it. There are other issues like there are no electronics, there's no power outlets available, and no remote control. So we have no diagnostic data. And there are very few solutions that exist that you can just apply retrofit to, legacy systems like this. Alumni Hall at IIT, which is our primary building that we did a lot of research on, they use cast iron radiators. And in fact, they also have asbestos in some of the places. So that was a prime example of what we can do and how we can use it to retrofit. So as we see, it's proprietary and expensive. Some of them actually use more energy, like programmable thermostats. Commercial controls actually take air temperature around the device into account. So, you have isolated heating and cooling, like it doesn't heat or cool the whole space properly. Some of the communication protocols between these building systems, like Modbus, the way they're implemented today, they lack data encryption. So if that's important to you, all of those matter. Some of them require installation of wires unless you're installing some newer version of it that has wireless, and then it's more expensive as well. The industry standard is BACnet, which is ASHRAE's protocol for building controls. But as we are today, they couple with protocols like Zigbee, which has like low range, long delays, bandwidth issues, and there are a lot of dependencies on like gateways and routers. It is slowly changing to a LoRa standard, and I think BACnet will, slowly get better because it is an open standard. So the objective of my research is to design and develop a suite of open source wireless sensors that we can, tackle these problems, to build a scalable platform for real-time monitoring, and also to demonstrate that we can do real-time data collection and analysis, and then use the same platform, which is hardware and software, to demonstrate building controls, specifically by retrofitting like existing building, and then perform thermal comfort analysis just to demonstrate that this can be taken further. It's not just energy savings, right? So open source, I'm sure some of you know about Arduino and Raspberry Pi. This is open source platforms that enable hardware development. In fact, some of those commercial sensors that I showed initially now starting to use these. These have enabled like rapid development of sensors and controls, and any new upcoming technologies, machine learning, MEMS-based sensing. These kind of tools really enable rapid prototyping development of these kind of controls. Quick literature review, there are some projects around the United States that have done it. For example, Conrad Hotel in Chicago, they've retrofitted and demonstrated that they can save up to $35,000 a year. Empire State Building in New York also has, they have retrofitted, I believe, a couple of floors, and they received LEED gold status. What they did was have automations based on all of these sensors, and they've estimated savings of $2.8 million a year. Of course, that changes depending, like Alan said, reality is different than what we expect, but at least there are some savings just by putting any kind of controls. There are other studies that have shown how to use these devices, like the Arduino kind of devices in scheduling, occupancy detection, even energy modeling studies that use Energy Plus models that use data from these devices to feed into your models. Now, I'm sure you've seen a pattern of all of these. Looks like it works. What do we do? So initially we started off by, all right, let's build our own device, right? So Sloan Foundation funded us to build this project called OSBSS, Open Source Building Science Sensors. So what we did was we built a collection of devices, which is the most common things that people want to measure inside buildings. And we made a whole tutorial of how you can build and assemble your own device, solder the board, how you can program it in firmware, how you can customize it, how you can measure all kinds of things. This paper is published in Building and Environment, and if you just Google OSBSS, you'll find a lot of information about it. So the next step is, of course, you can't sit and build your own, not everybody has the time or the skill set available to do all of that. So next evolution is we built this platform called Elemental. This is like a custom hardware and software platform. So let's try to harmonize it and bring it into something that's more automated and quick to set up. Like all the controls in one place, and it's going to be fully open source to allow like large scale implementation, right? So, and also more robust, like you don't have open wires and like just using any kind of random code that you find online. It's going to be like robust and ready to go. So this involves like board design. Basically, I had to learn electronic board, PCB layout design. We built our own suite of sensors, wrote the entire firmware for each and individual board. And we built a whole custom backend that not only monitors the data, but also displays it. And you can set custom rules and what we can do with this data. And you can customize it for each building, each room. Here's a small collection of all these sensors. We have, temperature, humidity, light, carbon dioxide, or anything else. But the whole idea was to build a platform that you can then tie onto and then keep, adding on as we go along. Quick specifications, because these are low power, they usually have a long battery life. 2 years is good for deployment in the field. You can always go back and recharge it. You can plug it in if you want, but running so many, it would get. But the good thing is it's wireless and it doesn't use Wi-Fi, Bluetooth, or Zigbee, which are more standard. It uses a lower frequency range, which allows greater transmission, which allows a better resiliency. You don't have interference from common devices like keyboard and mice. It has hardware encryption. And we also, in the paper that I showed, we compared the accuracy to existing technologies and showed that the sensors that we use and the calibration process that we used has been comparable to the commercial ones. And it's inexpensive and open source as well. So here's a quick simplified look at how this works. These are wireless sensors, right? So here, let's say you take a temperature sensor or a carbon dioxide sensor or whatever. You can take some other retrofitting technologies like radiator control, which I'll talk about in a little bit, and any other existing building systems like building control systems like thermostats or weather stations for monitoring or smart meters and things like that. All of these send data wirelessly on your network, and we have a backhaul that we've built using a Raspberry Pi that can take in data from all of these devices. So all those USB modules that you see can basically accept data from all of those. And just a quick cost comparison, if you look at like an onset If you want to use 3 sensors, that's $274 per sensor. Like you're looking at over $1,000 in many areas, but whereas our platform gives you like quite inexpensive, and this is for 5 sensors, right? It's $15 per sensor, and you get in $120 you can deploy and get data in real time, and we solve a lot of the problems that the other ones have as well. So you can now quickly see how easily it is to scale these. We have custom backend software that you can deploy in the cloud. We had it deployed in a tiny computer in our lab, but the demonstration was, it's a server, you can put it anywhere, and that stores all your data storage and your visualization as well. So you can connect to it by going to a website on your phone, and it just brings up all the data. We use a platform called Grafana to do real-time data monitoring. Some of you might be aware of this, but basically you can tie in any database and display building data or any kind of data, right? So you can set up to show like HVAC performance or any legacy controls, for example. The good thing about this platform is you can do data analysis because you have all of this data available to you in real time. What you can do is extract data and do very quick analysis. So for example, those people who know environmental engineers, you might know that air change rates, calculating that requires a lot of, you have to figure out the slope, extract a lot of CO2 data, figure out what the minimum and maximum is, and then finally calculate the air change rates. This whole analysis, this is 3 months worth of data that we extracted from there, and it took, using the web API, it took like a few seconds to process and generate these graphs and do the results. So that's really showing you the versatility of this platform. The platform also ties into residential smart home metering, which can just grab data from your smart meters, which is that rainforest automation thing. We also do fault detection. I'll talk about this in a little bit later, but the whole platform paper is published in MDPI Sensors Journal. So you can look at it. If you Google Elemental, you'll find the whole paper for you to look at. We're demonstrating building systems control application, which is the whole point of this, right? So how can we retrofit and try to see legacy building control? So radiators. We have radiators. We want to build control, so we deployed this on like 20 radiators in Alumni Hall, along with some of the wireless sensors that I talked about. This particular work was funded by a grant from People's Gas, North Shore Gas, and we're grateful for Adam DeSalt from Franklin Energy, who's also been supporting this resource for a while. Also funded by an ASHRAE New Investigator Award that was given to Dr. Heather Nejat, who is our panelist today. So a very quick overview of how that works. Radiators have an actuator and a valve. So that's a manual control, like you spin it, which has set point from 0 to 6, right? 0 means it's off, 6 means it's on. So let's 3D print a knob, attach it to a servo, and now you can spin the knob automatically. You don't have to do anything. So that's basically how the control works. Now let's build a custom board that can do the logic for you, put some buttons on it, put a screen on it, put everything in an enclosure. Now you have an automatic radiator control, right? So it's as easy as that. I say easy, it took a while to get to that stage, but now you can retrofit the old knob with our new automatic knob, right? This is like an exploded view of what it contains. Here's some setup pictures that show that we had multiple of these deploy all around the lab, all around the building. Our custom backend solution, we had to build because now you're growing in the number of devices that you're deploying in the field. So you have to develop like a backend solution that you can automate, right? So you can quickly set up any kind of set point or a start or end time or any calibration needed, or define the room, things like that. So we have like a very clean backend solution for that as well. Here's some more setup pics where we also used multiple sensors just for this particular study. In this particular project, we had control strategies that we wanted to experiment with and understand. So manual control strategy behaves like the original controller, but you have buttons and screen. Instead of turning the knob, you can interact with it, but essentially behaves the same. An enforced schedule is from 7 a.m. to 5 p.m. Heat is on to a set point and then turns off. Occupancy based, we use our motion sensors to understand if someone's in the room and dictate what to do with it. PID control, instead of using a set point like 0 to 6, we used a room temperature, and then PID plus occupancy just merges the two. And just to clarify, control node has 7 set points, right? 0 to 6, which is what the radiator knob usually has. We staggered each strategy. We basically randomized it during our study, and we took thermal comfort surveys to understand how the occupants are feeling in that period. Here's the floor plan. We basically wanted to cover north, south, east, west off the building. And on the right, you can see all the sensors that we used for this project. So our almost over 95 sensors that we built, programmed, and deployed. But as I showed, the cost is low, so you can see how we can scale a project this size, not just for study, but actually controlled as well. Here's some results. So on the left y-axis, we see radiator on percentage, and on the x-axis, we see each control strategy. So what we see is, as we go from a manual strategy to any kind of automation strategy, the energy usage or radiator usage decreases. And if you go to a very aggressive strategy, we see over 63% radiator energy savings, and there are good reasons for it, and I'll show you why. When we normalize the radiator usage with outdoor temperature, we see that, as expected, it follows a trend of increasing outdoor temperature reduces your radiator usage. Both the control strategy follow that. However, if you leave it at manual control, you can see that it doesn't really matter what the outdoor temperature is. The radiator usage barely changes regardless of it. So clearly manual control or leaving it over there is not a good idea. Other control strategies also followed a similar trend. We had some extremities due to the polar vortex that happened in 2019, but that we can also see that data here. So all control strategies followed a good, downward trend over here. We also noticed that people turned down the radiator more than they turned up. We were logging button presses and to see that, and because it shows that the radiators are too big for the heating zones, because they were designed like decades ago, and all the room layout has been changed since then. So clearly legacy systems are no longer applied to what we have today. So that's good information to know as well. We also tracked room occupancy using the sensors. Obviously there's no personal identifying information there. It's all anonymous, but we can see a trend of, people coming in at 8 a.m. and then leaving at around 5. Some rooms have greater, some have less, usage, but clearly you can't apply a standard control strategy to all of them. So this is good to know. You can have customized controls in each room. And we took thermal comfort surveys. We found out that manual control, most people were satisfied, but occupancy-based and any enforced schedule, people were dissatisfied, right? So it's a good observation. Why are people more satisfied in manual control? Well, if it's cold outside, let's say you're at 0 Fahrenheit and you walk into your room, you didn't turn the radiator off. As Alan observed, nobody, if you tell them to turn it off, they're not going to. So you left the radiator on running all night, it's heating up the room, you come back, now you come in a warm room. So obviously you're going to be satisfied with the usage. So what we did was, in our survey, we took during the day and in the morning, and we found out that people are satisfied generally more during the day than in the morning, because the controls are now working, as opposed to in the day in our automation strategies. In our automation strategy, the radiator is off, and then when they do come in, it turns on, right? So that's something we can solve by preheating the room and understanding data. So for thermal comfort analysis, we used mean gradient temperature. This informs you how people react to radiant heat coming from the radiator. Traditionally use a black globe thermometer. We built our own using a black ping pong ball stuck to a pencil attached to a mic stand. Worked just as well. There are equations that are defined by standard of how you can calculate it and estimate the mean radiant temperature using this kind of black globe to estimate the radiant effects. We also used that mean radiant temperature to do PMV PPD analysis, which by ASHRAE 55 standard, if you're aware, PMV stands for predictive mean vote, and PPD stands for percentage people dissatisfied. We use Pi thermal comfort developed by UC Berkeley. essentially, as close as you are to zero, that means the more comfortable you are, the more you stray away from it, you're either feeling hotter or colder. And PPD, obviously, as it indicates, the less people that are dissatisfied, the better. The higher means, there are more people that are not, they're thermally discomforted by whatever you're doing. So we found out that, using an enforced schedule from 8 to 5, most people are dissatisfied. And go figure, right? But when we do occupancy based, when we do temperature control based, people are generally satisfied because 72 degrees for them means something else for somebody else, right? So each person set their temperature set point to whatever they wanted, and they were more satisfied that way. We also measured the actual heat output. We used heat flux sensors, strapped them to the radiators, and just measured the heat output. We supplemented that data with the thermal camera just to see some thermal imaging and how the heat flows through the radiator. I don't know if this video is going to work, but this is essentially how you can see. This is a time lapse. Bottom here, the time is in minutes, but you can see the heat flowing from the right side here, flowing up into the radiator and then filling up. Surface temperature is quite high. You can see it's like over 80 C in some areas, but it takes about 20 minutes for the whole radiator to fill up. But by that time, you're already experiencing so much radiant heat that you don't really need it to fill up all the way, depending on where you are in the room, right? And then we turn it off. The video keeps going on. We turn it off, and it takes like over an hour and a half to come back to room temperature. So these are good things to know. And then finally, what we did was estimating the heat output from this. We used the Fourier's law of thermal conduction just to calculate the actual heat output coming from this radiator. The surface area varied, but like Alan said, go out, measure, take pictures. So we basically measured every single radiator that we put this on, and made some good assumptions about the U value and surface temperature. We measured all of these. So what we found out though is the average heat output was about 1500 watts, which is not different from your typical electric heater. However, this is average, right? It doesn't tell the whole story. This actually varied between 200 watts and 4,200 watts. So some of these can get pretty hot, and the room sizes vary so much that, in a small room, 4,000 watts, you can start sweating quite heavily, even if it's like extremely cold outside. We scaled it up. We developed a model to scale up these outputs. We tested on 19 radiators, but we scaled it up to 55, which is what the building contained. And we found out that if we use our aggressive control strategy of just detecting occupants and turning the output on, and when they leave, turning it off, we found out that if all radiators had our controls on them, we would be saving around $1,500 over your manual control in just a 3-week period that we did this study on. So now you can imagine how it scales up easily in the entire winter duration, and not just that, but for other buildings as well. Fall detection, I'm going to try to go quick here because I'm over time. Fall detection, if you set the radiator to if you set it to off and you expect the temperature to drop over time, like we showed the time lapse, it should go back to room temperature. But if it's still on over time, you can easily see that something's not right. The valve needs replacing or fixing, and you can quickly come back and address these issues. What we've seen realistically is if this system was not in place, it takes over a few weeks to a month for facilities to even be involved and address this issue, because people just think that's normal and they wouldn't even address it. They wouldn't even know that there's a leak until the temperature outside gets warm enough for people to feel uncomfortable enough for them to make a work order request. Whereas in our system, we can automatically say, you're off, but the surface temperature is high, send an alert when it's above a particular threshold. So you send an alert directly to facilities and they'll handle it. This whole paper is published in Energy and Buildings, so you're also welcome to go out and look more about it in detail. So a final summary, we can see that open source wireless sensors have great energy saving potential. Long-term data collection and real-time monitoring that allows a wealth of information to be collected and analyzed on a large scale. Retrofitting legacy buildings such as radiators are now possible, and integration with model platforms like how I showed the data collection and any kind of database. Now you can make decisions on things you couldn't have made before. Now you can also achieve thermal comfort at the zone level, and it can be customized to each individual, and over time you can prioritize energy savings or controls. A lot of potential here for anybody who's into modeling, where you can take all of this data and do predictive control, machine learning, and estimation of preheating or anything like that. But just having real-time access to so much granular building data allows for quick maintenance as well. And just a quick note here that this work was done, prior to COVID-19. So we had normal occupancy patterns. We don't know what normal is anymore, but essentially major changes in occupancy patterns due to the pandemic left so many buildings unoccupied or in a hybrid state, which actually further emphasizes the utility of such kind of automated control systems, right? Not just to save energy, but also to direct that energy to other sources. And now you can be more efficient about it. So yeah, that's it. Thank you very much. And I will pass the mic to Linn from HabLab.
All right. Let's see here, slideshow. All righty. Hello, everybody. That was super cool, Akram. Thank you so much for sharing that cool stuff. My talk today is about just one building with some problems. It has paintings that are trying to get frozen. It has interior gutters. It was built in the 60s. So I'm excited to tell you all about it. It's just a little case study here, and I'm Graham, as mentioned. So save your questions till the end, of course. So yeah, case study, existing building. There's problems with the envelope, HVAC system. I'll also take you through kind of process of investigating these issues, which both Alan and Akram have tested. It's a bit of an adventure, and then I'll show you something called a hydrothermal simulation, which I'll explain in a bit, and then also a little bit of sort of airflow through a tool we called CFD. So here's our building. This is in Madison, Wisconsin. It's called the Elvium building. It is, as you can see, a pretty darn stark looking outside. Only a few windows, built in 1969. Here's the interior, of course. Nice big atrium, big skylights in the top, and galleries that are kind of around the perimeter. And I also wanted to give you some of the context of this building. So it was built or designed by a guy named Harry Weiss, who is a somewhat famous Chicago architect. Maybe some of you heard of him. He's done a bunch of buildings in Chicago, and I think he's most well known for he helped design the metro system stations in the Washington D.C. metro system, if you've ever gone there. So notable building, historic building. Here it is. It's in front of there's a bunch of trees in front of it in this shot, but just wanted to give the context. At the same time as Humanity or Elvium was built, this building next door that's called Humanities was built. It looked, very similar design language, same architect. And this is somewhat infamously brutalist building. Unfortunately, super duper leaky and falling apart, and probably, I think, going to be replaced soon. Interesting note, the Elvium, the reason I'm talking to you is because they're trying to repair it, and apparently it has lasted longer. It's obviously probably partly design specifics, but also they had more money because it was privately funded even back in the 60s, whereas the Humanities building was a public building. So you can see, penny wise, found foolish. This building could have survived if maybe they'd spent a little more money. I don't know. And then next door, of course, is this Chazen building. So this is an art museum. The Elvium is an art museum. They're all one thing now. There's a skywalk. If you visit, it's just called the Chazen. So anyway, that's some interesting context. And so here's our building, though. So it's like I said, not many windows. You've got some pyramidal skylights on the top, but then one of the things that's surprising is there's actually a bunch of skylights on the side too. This just looks like roofing, but it's actually sloped skylights. So I'll show you a little bit how this works. Here's what it looks like inside. These are the galleries. The skylight is coming down into the space. You can see the quality of the light a little bit better here. But the way this works is you've got that sloped roof, there's a skylight, and then it kind of, it's kind of a borrowed light. There's this grid with some plastic to, and anyway, the light comes down from the outside through the grid into the space. So just a really interesting design. But what it creates is this really awkward interstitial space that I just call the skylight zone, kind of in between the gallery and the roof. So that's the context. What's going on? Why are we talking about this building? Well, there's a bunch of things going wrong. This obviously looks bad. The exterior cladding, all these joints have opened up. Don't ask me the specifics of why these materials apparently aren't working right. There's a whole very detailed materials report about that. But obviously this is something that they want to repair for the longevity of the building. Now there's lots of interesting other things going on. So we have a whole bunch of interior condensation happening. So this is a shot of some of those top pyramidal skylights, and on the right is some of the slope skylights. I think that's condensation there. Anyway, we have reports of lots of condensation happening. And this has actually been happening since they first designed this building. And in fact, that was anticipated. And from what I gather, this isn't too uncommon for some skylight systems. They have interior gutters, so if condensation happens, water might start dripping down and end up in one of these gutters. Obviously, there's water happening here. It's discolored. It's kind of gross looking. But unfortunately, it was not really adequate. So this is a slightly different shot. This is this awkward interstitial zone. They actually, here's like where the gallery is. They had to put plastic down almost immediately because it was raining in the gallery back in the 60s. So they've tried to fix this before. In the 90s, they added interior gutters on the upward slope, which don't really look like they get much use, to be honest, which gravity might have predicted that, but I don't know. And they also added some HVAC just to serve this weird interstitial zone. So yeah, that's some of the issues going on the outside. And then we've got even more. So this is obviously artwork. It looks like it's melting. Not good. Well, what's going on is, thankfully, this is just something going on with the wall paint, not the painting. But it gets so cold, the interior wall freezes, it frosts up, and this causes this regular old latex paint to decompose, which is something I had never heard of, but it was a major issue, obviously, and we'll see why in a sec. So major issues there. So the process of investigation. So we're looking through this building. We're like, why are their walls so cold? On the drawings, it looks like there's insulation, and this is pretty progressive for a 1969 building to have this nice board insulation, and it looks like it's continuous in the drawing. Well, it's definitely not, as you can see. Here we opened up the wall, took the limestone block out. We've got this is just the concrete block is the main structural element. But this is our board insulation, and as you can see, it is definitely not continuous. And in fact, I would describe this more as like a Connect 4, not particularly thermally effective, unfortunately. So you can see, why the interior wall would get so cold when the thermal control layer and air control layer are basically absent. So not good. We also got pretty sidetracked trying to figure out if there was interior insulation. We had seen a bunch of conflicting reports, so many reports. We started opening up walls, and we were just shocked. Like, look at this. This looks like brand new, recent, nicely installed insulation. And we were just really scratching our heads. And it turns out we were just looking in the wrong place. They had at some point, probably when they built its neighbor building, and they built that skywalk, they came in and did a bunch of random stuff. We found no documented evidence for this work, but they installed just in these little storage rooms this interior insulation. The vast majority of the walls are not like this. They are just like we see on the right. And the lesson was, it was convenient to look inside the walls in the storage room, but it was not representative. So we figured out what's really going on. We've got concrete block, plywood, which is an issue, and then gyp board and paint. So that's the true interior wall structure for the vast majority of the wall. Okay, so we've identified some of the actual issues with the envelope, but now we got to talk about the HVAC. So this is a big scary psych chart. What we have here is temperature left to right, and then we have like humidity top to bottom. So the staff, they want this nice golden quadrangle. I'm not sure what the right name for that shape is. You know, they want the temperature inside the space to be somewhere between like 65 and 75, and then they want the humidity, this is relative humidity, to be like, oh, you know, between 40 and 50%. That's what they want. Unfortunately, the system, the actual system, you follow this chart, these lines, it takes the cold air in, this is a winter condition, heats it up, even does add humidity. They add humidification, and then it gets in the room, but it's just barely on the corner here. So this is not good. HVAC is not performing well. Unfortunately, our scope is supposed to just be fixing the exterior of the outside wall. So HVAC is only tertiary, but it's obviously, as you can see, hugely influential. All right. Another major issue, just as an example, one air handler, one air supplying unit shoves 13,000 CFM in the space. And the way these work, it's fairly primitive, but was pretty fancy for the time. There's little fans that pull the air out, but the difference, 13,000 coming in, but only about 5,000 coming back out, 6,000. So we have 7,000 CFM just in this one zone that is unbalanced, is not being accounted for. It is pushing its way out of the building. And there's evidence of this from the door standing open. You can feel the air coming out. When we open the wall up, you could just feel it blowing you in the face. It's really something. So obviously a major issue. But you know, the main scope, as I quickly said before, was just what we call a hygrothermal analysis. So what does that mean? What is a hygrothermal analysis? So it's basically looking at both temperature and moisture inside of a wall. So here's like a wall section. This is just an example. You know, left to right is distance in the wall. The inside is on the left, and then you have this example. There's some insulation, some kind of board, and you got this looks like shingles or something. And the point is, in a hygrothermal analysis, we are looking at the temperature and the moisture through this section. So on the inside, it's obviously warmer, and then it, you know, this is in a winter condition, and then it gets cooler and cooler and cooler and cooler until you're at the outside. And so what I really want to emphasize here is that what's super duper important, if the whole point of this is, does the wall get cold enough that the moisture in the air will condense inside the wall? That is the whole game. So, you know, the point is, you don't want that to happen. You don't want moisture to condense inside of the wall. And, you know, if it does condense, you want it to be able to escape. But the principle is trying to at least set it up so that it doesn't condense, hopefully. So you can do simulation to try and understand this problem. Here, I'm giving you an example. So this is, we already kind of went through the existing wall where we've got limestone, air gap, supposedly continuous insulation, concrete block, a little gap, plywood, which is not good, and gypsum. Plywood is not good because it blocks moisture transfer. So we proposed, we were just sort of like we need a starting point. Well, we definitely want to add a proper air-water barrier. That's this pink magenta line here. This is to keep everything from moving through the wall. We want the water and air to stay on the outside. It's already outside, and on the inside, it's already on the inside, you know. And we also, you know, proposed taking out that plywood because it acts as its own vapor barrier, and so it could really trap some stuff here. And we'll see. This is just comparing those last two things I showed you: keeping the plywood, removing the plywood. So this is like top to bottom is how much moisture is in the wall, and then on the bottom left to right is time, how many years. Now they measure these things in years. These processes are slow. You know, this is just to give you an example of the issue. If we take the plywood out in orange, boy, this looks great. It comes right down and then it hits what we call a nice equilibrium. So it's basically as dry as it's going to get. Sorry, I should preface that. What we have, we assume like something bad happens. We have like a fire sprinkler go off or some part of the envelope fails and it leaks. If we get a bunch of water in the wall accidentally, we want it to be able to dry out. So we're watching that potential drying process. So as I said, removing the plywood, it gets to an equilibrium after a couple of years, but if you keep the plywood, it's not even at an equilibrium after 5 years. So that's the major issue, a major issue. Next issue is trying to understand, like I said, where is that wall cold? So what I'm analyzing is right here, because we know this is going to stop vapor and water from moving. Okay, this is this pink line, the water vapor. Okay, so we're going to study, okay, how cold does it get there? Does it get cold enough for it to freeze or to, not to freeze, but to condense? And it depends on how much humidity you have. And in our situation, we know we need more humidity because of the gallery and the artwork. So we have a kind of a high, what we call a dew point limit. If that temperature at that pink line ever gets below 50 Fahrenheit, we're going to get condensation. Not good. Not good. So this is an example. Unfortunately, this profile I'm showing is for 1.5 inch insulation, and it gets pretty cold. It's not acceptable. So our next proposal, I mean, we tried a lot of things, trying to look at, all right, instead of 1.5 inch of board insulation, let's do 4 inches of closed cell spray foam, very high performance. It acts as its own barrier. There's no pink line because it's kind of integrated into this spray foam. And lo and behold, much better. The temperature right at where the insulation meets the concrete block stays above 50. And so this is an improvement. Now I will say that the owner has been very reluctant to commit to spray foam, trying to figure out how we can do this with regular board insulation, and now they're trying to compromise with the occupants to, like, can we reduce the moisture in the humidity in the space? So it's complicated. We're helping them through that, but that's the gist. And then one more thing to kind of really dial home the improvements here is, here's like cold air. This is like a pool of cold air. This is the existing gallery, existing wall. As we said before, the walls get super duper cold. And that not only is the wall cold, but there's also just a big pool of cold air, which is not comfortable. And so that we did, this is just an airflow simulation using CFD. And then on the right, we have, okay, let's improve this. Let's actually seal up the wall so it's not a Swiss cheese wall. So we actually have a proper difference between the outside and inside. And lo and behold, it does get a little cold still around the corners, but nothing like it was before. None of this super cold, freezing condition. So, significant improvement. So let's see. One more thing, I wanted to talk about these skylights. So the original skylights, especially the sloped roof, this was pre-energy crisis. These are single pane skylights. There's no thermal break in their in the frame. Okay, so hopefully we have modern, awesome new products, right? Well, here's this new product we want to try. Here it is. It's got double pane glass. That's the glass in the blue. The black is all the aluminum framing. And then we have this really nice thermal break. I put it in red here so you can see. Look at that. We're breaking the air can't, or the cold can't reach the inside. So hopefully we don't have so much condensation. Well, once you start analyzing it, you come up with some unfortunate conclusions. I have this set up in three scenarios here. There's the old scenario, the existing single pane glass. Then we have the new skylight, which is supposed to be great, but still with that existing bad HVAC. And then finally a scenario where it's repaired HVAC. So, on the far left, lots of hours. This is hours of condensation happening. That's an easier way to think about it. You've got lots of hours happening. We already know this. We've seen the evidence that the existing thing is not good. In the new situation, all right, if we just replace the glazing, all right, or the framing glazing, way fewer hours of condensation on the glass, which is great. That's that double pane glass. It's doing a lot better job. Unfortunately, that frame is still not very good. There's still many hours, even with the thermal break. So the lesson is apparently this had to be a very custom styled skylight, and that meant very, very few options for frame products, which is very unfortunate. And apparently it's better in Europe, which is so often the case with building performance. But you know, I do hope that maybe this is something that can be improved. If you buy a packaged skylight, apparently it can be better here. So, but then to really drive the point home, guys, like, you know, we need to repair this HVAC system. If we repair it and we don't have so much imbalance and moisture going everywhere in the wrong places, you know, that alone will drastically reduce the amount of hours that we have this frame condensing, you know, basically none on the glass and very few on the frame. So that's the story. You know, lots of things failing. What's nice is the existing building envelope is kind of well suited. It already has a place to put insulation. It's already kind of set up. It just needs to be fixed so it doesn't look like Connect 4. And we got to get that interior plywood out of there. But this existing building is kind of got a good bones to become a high performance building. But you just you have to think through the different elements carefully. You know, we can see that the repairing the envelope will improve conditions. You know, we saw that in the skylight, but ultimately that HVAC system needs to be repaired or replaced. It's original. I should add, it's original from 1969. It's quite lots of belts and loud fans and things rusting. So it's quite a sight. And then finally, the custom skylight solutions are not great. So that concludes my talk. There'll be questions in a second. I'll hand it back over to Jed as our panel moderator.
Thanks, Graham. Great presentations, everyone. Graham, we'll just start with you since you've finished up here. Your example's pretty interesting. What was the most interesting thing that you took away from your modeling?
You know, just that this, like I kind of was just saying, that the wall structure is already kind of well suited. This isn't, you know, this is a relatively new historic building. A lot of historic buildings, it's just a monolithic bunch of brick, and like, what do you do with that? How do you add something to that or improve that? But this situation is potentially quite good, but just has to, you know, you have to understand what your needs are and dial in your insulation levels. So
Right, yeah, the building the model and doing analysis before you build it to be able to find it out is really awesome.
Yeah.
Yeah, and then I guess on that note, Alan, how's your building systems with those buildings play in and help you make better informed decisions?
Obviously, simulation is a tool, and for my projects, the owners, especially the office building, it's driven by the local laws and building performance standards, and the model is a critical piece to show compliance down the road, basically. Which is very important in a lot of large jurisdictions in the US. And my study, it kind of like a sensitivity study, you know, like what if you do this, what if you do that, what's the impact, and how much penalty you can avoid. And it's very challenging because we were talking about dollars, like very upfront. Like, if I do this, how much money I pay for the penalty? If I do that, how much is a dollar. So so I guess my model in terms of it's not it's a retrofit, but really it's a compliance type of scope.
Well, Akram, wanted to ask, what are some of the limitations of your devices on large scale deployments?
So the device that I showed, basically that was hardwired, right? It had to be plugged in, and you won't always find in the field, especially in legacy buildings, right? You don't always find available power. So sometimes you have to think a little bit more creatively. Like the limitation over there was hard power. We are working on a second generation of that device where we're getting it battery powered. We did have a few potential installs. People were interested in getting it installed in certain buildings where they said, hey, we want to use your control. We have this particular type of valve and these old radiators from like 1930s and 40s, but we don't have outlets and we can't run extension cables everywhere. So what can we do? So we have some interest over there. So we're trying to get it battery powered, and data storage is also another issue, but that's quite easily solved. It just depends on the kind of solution that you're looking for.
Sounds good. I guess the big thing here, I think we're talking about is collecting information and pulling it together. Just general question to all three of you guys. With existing buildings and challenge of collecting data, what do you think some of the best things moving forward to help you get the most accurate data energy models is helpful?
I can answer that question. Collecting data is very difficult. If it's just meter data, on the building automation system or data logs, and sometimes the utilities have data, they have metering data as well. Those often you can get those, right? You can get those. But in terms of some other information like how people use their space and how the occupants, how many occupants and how many lighting fixtures, how many commuters, basically what is the load, that information can be very difficult. That's why I mentioned in my presentation, you're not going to get all of those. You're not going to get all of those. You will have to make some assumptions, and those assumptions sometimes can be very critical. Let's say, if you model an office building with a receptacle load at 5 watts per square foot, is that reasonable? You're not going to get the information, by the way, most of the times. Is that reasonable? It is not reasonable. But in this case, it was reasonable because they were running servers 24/7. So again, collecting data can be challenging. So that's why my opinion is talk to the building engineer. The building engineer knows who complains and who has issues in their tenant spaces, and what is the history of that tenant space. The building engineer often has that type of information. So I think communication is key. Communication is key.
Yeah, absolutely. And I'll just add that the data gathering phase, I mean, I don't know how to possibly expand a person's scope or just to plan around it taking a long time, you know, like it's not like a new building where we're just inventing all these numbers and everyone is on the same table. Like it probably took us almost a full year to gather all the data we needed. And part of that was some bureaucracy challenges, but just the sheer quantity of it and trying to sift through it. And you know, it isn't necessarily that intensive, but boy, if you don't give yourself the time, then you're not going to be able to come up with a very good answer. So I don't know.
And just to add on to that, that was the whole motivation behind my research as well, where because data gathering is so challenging and analysis so challenging, what we really tried to do is build a platform that allows you to kind of ease that process a little bit and have like a standardized data set right across all of it. But you know, the experience really counts. And Graham, I think you can kind of add on to that. Is the more you do it in multiple buildings, the more you kind of go like, okay, I know what to look for. I know the kind of challenges we might face, but you also don't know what you're going to face. But at least with experience, you can kind of, you know, ease that process a little bit.
Yeah. Hire somebody like Alan or Akram or me that have experience.
Alan will tell you exactly what to do.
Yeah, I think what we really wanted to drive home here is there's lots of great data available and ways to dig through it in modeling, but you've got to find the right data, and collecting it and pulling it all together is a challenge. We're gonna continue on this similar subject of looking at more ways of technologies and modeling. So I'm pretty excited moving forward on that.
Also want to add on to that you should also know, just because you collected data doesn't mean it's good data. So you should know when to sort through data and what data is valuable. A lot of data doesn't mean it's good data. You know, you should know when you're wrong, and you should know how to assess the fact that you're wrong. And just because data goes in a trend, you should always have some ground truth to compare it to. You know, calibration is important. So.
Well, can you guys hear me? Awesome. Thank you so much to the whole panel, to the moderation. Akram, I feel like you just gave a final great takeaway for the audience. Does anyone else have any final comments? If people learned one thing and wanted to remember one thing from your presentation today, what should they go and do next? I'll come back to you, Akram, if you have another thing, but what you said was just great. But Alan, what do you think?
I think my takeaway is technology is moving forward very quickly, and our industry is very behind. And in my opinion, sometimes Google could be a little bit more adventurous and progressive in terms of adopting some new technologies in our industry. Just think outside of the box, I think.
Graham? Do you have an extra comment?
Yeah, I would just say if you have an existing building and you're like, you want to make it better, energy efficient, fix some problems, like you can't consider different parts of it separately. Everything is interrelated. So, you know,
unfortunately, maybe your scope, it costs a lot of money to fix everything. So it takes time to think through, but one affects the other pretty dramatically. So thanks.
Akram, do you have anything more to add? I didn't want to cut you off early.
No, I'm good. I basically, these two, Graham and Alan, said the same thing I wanted to say. So.
Awesome. Well, thank you guys all again. Thank you, Mohammed and Jed, for putting together this wonderful panel for Illinois Green. Thank you, Alan, Akram, and Graham, for sharing your expertise with the group. We will follow up with a email by the end of the week with a recording, some extra resources, PDFs of the presentations for you guys to dig in a little bit more. But want to thank you again for attending our last education program of the year, and hope to see many of you in person at the holiday party next week, December 15th at Bottom Lounge. Thanks and have a great day.
Thank
Bye.
you so much.
Thank you. Thanks, everybody.